they develop their codes and how they access or use temporal and spatial locality. Maybe can you just summarize quickly what the lessons learned were in that case?
So when we look at temporal and spatial locality, we mean of errors and failures, right? And sometimes it is the case, as it was in Titan, where an application would heat up a certain part of the machine because they're using just the GPU so massively. And then you would run into overheating problems that then create all kinds of problems within the GPU. So one of the last year's mascots and this year's DSN paper was actually about the correlation between power consumption, heat production, and the increased soft error rate on GPUs. We actually do see bit flips in GPUs just because the GPU is too hot. Right, so that's, for instance, one correlation we see. And that has a certain spatial but also temporal component to it. Right? But we cannot then now go to the application person and say, yeah, just distribute your application. Right? Because that just means that you now basically are at compute nodes that are far away from each other. And now you're paying the performance penalty for that. So what we want to do is provide the feedback to mostly the system designers to design the systems better. And then fill out all the different individual voids that are still there with maybe system software, maybe programming models that allow them to hide things. So for instance, one aspect which I didn't talk about in this talk because it's still a little bit an iffy problem is that we saw a lot of GPU failures on Titan. On Summit, right now, we don't even look at the failures because the system is just operational, but Summit has 50% more GPUs. What if we see a significant amount of GPU failures in Summit? How does that impact applications? We have 6 GPUs per node. If you see a single GPU failure, we basically lose 6 GPUs maybe at the same time. We have no programming model right now to deal with that. We're basically falling back to checkpoint restart. And losing a job because 1 out of 27,000 GPUs failed is not really a good programming model.
As Professor Sunita mentioned, I'm Robert Searles from the University of Delaware, and I'll be talking today about abstractions and directives for adapting wavefront algorithms to future architectures. So just some background motivation for our work. Parallel programming is the future. Government spends hundreds of millions of dollars building supercomputers like Summit, pictured on my slide, which means that we have to take advantage of all the acceleration that these particular types of machines can offer with things like GPUs and other heterogeneous architectures. Currently, existing state-of-the-art abstractions handle a lot of simple parallel patterns well. So the typical case, you'll see people give you a matrix multiply example or things of that sort that are relatively straightforward, or some basic recursion, master-worker tasking, these types of things that are already well-researched. But complex parallel patterns such as wavefront, what I'm going to talk about today, can prove to be more of a challenge. So the contributions of our work are I'm going to be presenting an abstract representation for wavefront algorithms, a performance portable proof of concept of our abstraction using OpenACC on a real-world production code used by Oak Ridge National Lab, and an evaluation of that proof of concept on multiple state-of-the-art platforms, and a description of the limitations of existing high-level programming models and how we can overcome these limitations. So just some general background for people who might not be as familiar with heterogeneous systems. There's several ways to accelerate your applications using these types of systems. There are libraries which provide drop-in acceleration, so you can call out to, if you've ever used a deep learning framework like TensorFlow, or if you're going to use any linear algebra solvers like cuBLAS, you sort of feed it in some data, tell it what algorithm you want run on your data, and then it will run that on whatever hardware is available, whether that be a GPU or another type of multi-core system. There are programming languages, so I'm sure everyone has heard of CUDA from NVIDIA, which is a pretty low-level language, but it provides a lot of functionality and flexibility. You can directly interface with your hardware. You can tell your code exactly what you want it to do and when you want it to do it. And then there are directives, which is what I'm going to be focusing on today. So basically, we're talking about an extension to an existing language, so you don't have to actually learn a new language or re-implement your code at all. You just sort of annotate your existing C or Fortran code and tell it what your target architecture is, and the compiler will generate this code for you. So the two most common directive-based programming models are OpenMP and OpenACC. By a show of hands, how many people in the audience have used either one of these before? Oh, okay. Almost everyone. Good. So OpenMP is a multi-platform shared multiprocessing API that since 2013 has started to support device offloading for heterogeneous systems. And OpenACC, since its inception, was a directive-based model for heterogeneous computing. So I did have a little example just in case we had anyone who wasn't familiar with this kind of programming model, but it seems like everyone is. So just real quick, if we had a very basic loop like shown on the slide, and we wanted to run this on our GPU using OpenACC instead, we would add a directive, and it would tell the compiler we would like to run this in parallel on our GPU. And if we were to do this in CUDA, it would look something like this, because we'd have to do all of our memory allocation, all of our memory movement, launching the kernel, all these things verbosely and explicitly. So, as I mentioned before, these models already handle simple parallel patterns pretty well. So we saw that for loop that I showed. It's relatively simple. There's no data dependencies. It's an embarrassingly parallel loop that is very trivial for the compiler to generate GPU code for. But that's not typically what you see in production codes. When you actually move from synthetic benchmarks into production codes, you see more complex behavior, data dependencies, potentially different threads trying to write to the same location in memory. That can require either manual code rewrites or additional functionality. It's not as trivial to implement these types of things, so we need additional features and extensions. Well, a large portion of our work is how do we actually identify that, and then how do we move forward into actually creating these additional features and abstractions that we can integrate into these models. So as I mentioned, I was going to talk about a case study application that is used by Oak Ridge National Labs called Minisweep. So Minisweep is it's a mini app that basically represents the main sweep kernel of the de novo radiation transport code, which is used to model nuclear fusion reactors. So, and specifically, it has been used to model the International Thermonuclear Experimental Reactor, or ITER. The goal is basically, the way that the domain scientists use this application is they run it many times with different parameters. The faster it runs, the more configurations they can explore in a fixed wall time. It poses a multi-dimensional problem, 3-dimensional in space, 2-dimensional in angular particle direction, and 1-dimensional in particle energy. So this isn't as simple as a single loop nest that we need to parallelize. There's a lot of different things that goes into this particular application, and we want to be able to run it as fast as possible so that we can explore as many configurations as possible. The code status, when we originally started talking to Oak Ridge and working with Oak Ridge on this, is available on Wayne's GitHub. It was selected for early application readiness on Titan when Titan was being built, and it is currently being used for